Problem 3349. Reschedule meetings for maximum free time 1. To solve this problem, we need to know two concepts. One, sliding windows, and two, greedy. Greedy is all about thinking optimally, and sliding windows is exactly what it sounds like. Given an array, we have a window that slides left to right or right to left. It basically maintains a subarray and updates that subarray as we iterate through the array. And let's see how this plays out in this problem. The problem criteria basically is we are given an event time, and the event time basically is the interval in which sub-events happen. So event time is equal to 5, so all events happen between times 0 and 5. We have start times and end times, and the corresponding elements basically represents to a corresponding event. So at index 0, what that's saying is that event 0 starts at time 1 and ends at time 2. At index 1, it corresponds to event 1, and it tells us that event 1 happens at time is equal to 3 and ends at time is equal to 5. So that's the whole idea. And we want to basically move at most k events, in our case k is equal to 1, such that we maximize the amount of distance between two consecutive events. In other words, we maximize the free time. So originally we have event 0 here, and we have event 1 over here. And the way we solve this is we simply shift event 0 to the left by 1 space, in which case we get this to be here and event 1 to be here. So originally the gap here was 1, but now the gap here is 2. How do we solve this problem using sliding windows? Well, the objective is to maximize the amount of free time. So it would make sense to let the window represent the amount of free time in that window, and we want to find the window in which we have the biggest free time. But what is contained within each window? Well, let's give ourselves an example here. We have event 1, we have event 2, and we have event 3, and let k is equal to 1. A window, in our case, is therefore going to have the following properties. It's going to always include, at most, k is equal to 1 events within the window, and it's going to begin at the end of the first event, and begin at the end of the first event, and the window is going to end at the beginning of the next k plus 1 event. So if that didn't make sense, let's just try to solve this problem. It doesn't matter where they begin and end. It's just for illustrative purposes. So at the very beginning, when we're considering, hey, look, how do we solve this problem? We always begin at time 0. At time is equal to 0, well, we're only allowed to shift at most k events. So within the window, we can, if the window is of length, or rather, if the window is of length k, it means that we can shift the k events within it however much we please. So because, in our case, k is equal to 1, the window has a size of 1 in the sense that it contains one event and one event only. It cannot contain event 2, for example. And in that window, event 1 can shift however much as it pleases. And optimally, we always want to greedily shift it to an endpoint. And it doesn't matter if we shift E1 here or if we shift E1 to the left endpoint. What ultimately happens is these two spaces become 1. And in doing so, we maximize the possible free time in that window. And we basically calculate all these windows until we find whichever one gives us the greatest contiguous free time. So let's apply this concept to the problem we just solved using the window idea instead of just using pure intuition. So we have the number line that looks like this. Event 0 happens here, event 3 happens here. K is equal to 1. We are only allowed to move at most one event, so every window should contain at most one event, only one event. So we want to include as much free time to be merged as possible in this window. And that, therefore, is going to always be starting off at 0 and then ending at the k plus 1, at the start of the k plus 1 event. So here, this is the first event, so therefore, the window should end at the start of the second event, right? That just makes sense. So here, we can shift E0 however much we please, but the end result is always going to be the same. It doesn't matter if we shift E0 here or if we shift E0 here. What ultimately happens is we are left with a free time of 2. Therefore, that amount of free time is going to be equal to, if I call this the right and the left point, the right minus the left minus the number of events within the window. That is equal to the amount of free time. And we want to find the max of it. So at the very first iteration, when we consider just this window here, then we have a free time of 2. That is the maximum so far. Now let's shift the window. But how do we shift it? Well, it's the same idea. If I were to extend this out, then the window, the next one, would logically be right here, right, where this corresponds here and this corresponds here. Because again, we want to merge as much free time together as possible. So the window should start where the previous event ended, and if this were another event, the window should end where the next k plus 1 event starts. That way we merge as much free time as possible. Here, in this window of size k, we can shift E3 freely, either here or here, but the end result is going to be the same. We're going to get a certain amount of free time left, and if we were just to cut it off at 5, where there's nothing to the right of it, then the window would just end at end time. And here we only have at most 1 free time, which is to the left here, and that has a size of 1. 2 is greater than 1, so 2 stays as our answer. So that's the whole logic, and we can program this up in Python. So we're going to need to iterate through every single event. So n is going to be equal to the length of start time, because for every 1 start time, it corresponds to 1 event. So n is this. You could also do end time, but same length, same thing. Now, since we're iterating through every single event, we're going to keep track of how long the events in the window are within t. And this will all make sense in a bit. So for I in range from 0 to n, we're going to what? We're going to add the duration of the current ith event to t, which is the end time of I minus the start time of I. That's the duration of the current event. But why are we doing this? Well, because every single window is going to contain the duration of the k events within it, and that's needed to calculate the free time, which is the right endpoint of the window minus the left endpoint of the window minus the number of k events in that window. So that's what we have to have t. Now, let's set the right endpoint of the window. What is that going to be? Well, think about the extreme, where we're at the very last element, the very last event, and that's indicated when I is equal to n minus 1, because we're iterating through every single event here. When it's equal to the last event, the right endpoint must be equal to event time, because we're trying to merge or in the event that we have k is equal to 1, we're trying to merge k plus 1 spaces together. And there potentially is a space to the right of the last event, which is going to extend all the way to event time. And if the last event finishes at event time, well, that's perfect. We just still have event time. So that's why we have that. And otherwise, we're still in the middle of the entire events. And right is going to, so the right, meaning the end point of the window, is going to end where the next event is going to start. So where is the next event relative to I? Well, it's the start time of I plus 1, right? The current ith element plus 1 gives us the element right after I. So that's the logic here. Now we can start setting the left endpoint of the window. And well, if we're setting the left endpoint, that means the window is shifting. The window cannot start shifting until it has grown to a size of k, meaning it has contained k events within it. How do we know when it has contained k events? Well, when I is equal to 0, we have stored 1 event, because we added 1 event to t. And when I is equal to 1, it becomes 2 events stored in t. I is equal to 2, we have 3 events stored in t. So what this means is when I is equal to k minus 1, we have stored k events within the window, and the window can start shifting. So if I is greater than k minus 1, then that means if we do not start shifting the left endpoint, we are going to have a window of size k plus 1, k plus 2, k plus 3, etc. So when this is the case, the left endpoint has to get shifted, but get shifted to where? Well, the left endpoint, the starting point of the window, is going to start where the end of the previous event relative to I ended. So that's going to be the end time of I minus k. I, remember, represents the rightmost element in the current window. I minus k basically skips back k events in the window and gets us to the event prior to the leftmost point included in the window. And otherwise, it means the window has now grown to a sufficient size, so left stays put at 0. And to illustrate this idea of the left endpoint, consider event 0, event 1, event 2, event 3, and we have k is equal to 1. So we can only have a window containing 0, 1, 2, etc. But we know that, let's say the window containing 2, when we're considering 2, the window containing 2 must start where event 1 ends. So we access event 1 given I is equal to 2 by just doing 2 minus k. In other words, I minus k, right? I is equal to 2, in our case, k is equal to 1, so that's equal to 1. So it gets us the endpoint of the event immediately prior to the window containing 2. So that's why we do I minus k for end time. So now that we've said right and left, what do? We now have to check if our event condition is satisfied. If I is greater than or equal to k minus 1, it means we've reached a sufficient size where the window is of size k. So we can start updating res. Res is the max of the res result, the current result, with the current free time in the current window, which is right minus left minus t. And with that, what can we also do? Well, we need to, once the window is shifting, t has to get updated. T gets updated how? As the window shifts right, we are basically getting rid of an element. So event. So 0, 1, 2, 3. Event 0, 1, 2, 3. Start event 0. We move to the right to include event 1. Now we're getting rid of event 0. As we're on event 1 and we shift to event 2, we must get rid of event 1 from t. So how do we do that? Well, t minus equal to the right of I minus k plus 1 minus the left of I minus k plus 1. And that makes sense, right? Because I minus k plus 1 is inclusive of the last endpoint. So going back to the example, event 0, event 1, event 2, event 3. Consider we are at event 1, and we are shifting now into event 2. Well, I is currently at 1, k is equal to 1, right? K is equal to 1, and we're currently at I is equal to 1. So 1 minus 1 plus 1 gives us 1, which is exactly the duration of event 1 that we need to get rid of. So it's inclusive of the event that we are just about to ditch, which is why we do I minus k plus 1. I minus k gets us, for example, all the way back to 1 if we have consider of size 1 here, and we're considering 3. If we're considering window 3, I minus k takes us back to 1, and then adding 2 gives us back, it goes up by 1 spot to include that event that we need to get rid of. So that's how we do t minus equal to that. And with that, we're basically updating the window now, so everything makes sense, and we can just return res when all the windows have been determined and res has been updated appropriately. So let's run it and see what happens. And error cannot access local variable res. Did we not declare it? Oh, so res is going to store the results, so res is 0. That should work. Int object, oh sorry, this should be end time, and this should be start time. There we go, it passes, so let's submit. And that's the solution.